All right, now on to the second half. Here I have two graphs, and these are the two graphs that you should have got to in order to answer questions 3 and 4 from above. So the first graph that you would make is pressure versus volume. And you see this curved line that goes like that, and you should be thinking to yourself, this looks like it's inversely proportional. So you say to yourself, oh, okay, well, what should I do? You should make a graph of 1 over pressure versus volume. And you will see a straight line that goes more or less through the origin. All right, so what information can we gather from this? We can say that as volume decreases, pressure increases. And what mathematical relationship then exists between pressure and volume? They are inversely proportional. Done. Simple. So, here we go. As volume decreases, pressure increases. So we can say that pressure is inversely proportional to volume. Now let's logic that out. We've got our sample of gas in here, okay, in our syringe, and we decrease the volume. All right? Now, that means that the amount of empty space between particles is going to decrease, which means that there are going to be more collisions with the walls of the container, which means pressure is going to increase. So let's take a look on our little simulation here. Okay, I'm going to make the volume of this container smaller. Okay, and there are more collisions happening more often. Okay, so I'll expand him back out. All right. And hopefully you remember how to go from a proportionality to an equality. So see if you can take this all the way to the gas law. Pause it. See if you can take it all the way to the gas law, just like we did with Guy-Lussac's law, and then resume and see if I get to the same place. So remember, when you go from a proportionality to an equality, you add a constant. So P equals 1 over V times K, which means that I can say that P times V equals K. So the pressure times the volume in this first syringe, in this first instance, should multiply to the same number that the pressure and the volume, the multiple of the pressure and the volume in the second case. Okay? So I can say P1V1 equals P2V2. Thus, P1V1 equals P2V2. And this is called Boyles Law, named after Robert Boyle. All right, so let's take a look at what a sample problem with Boyles Law would look like. All right, here I have, I'm just going to move this down a little bit so I can mark up and draw. I'm going to highlight as I go through. A helium-filled balloon contains 125 milliliters of gas at a pressure of 0.974 atmospheres. What volume will the gas occupy at standard pressure? Okay, so first thing I'm going to run to is the volume, all right? And here's my other volume. What volume? So this is V1, and this is V2, and this is what I'm trying to find. Okay? Here's my pressure, 0.974 atmospheres. And here's another one, standard pressure. So this is P1, and this is P2. Now, pause it and see if you can remember what standard pressure is. Standard pressure is 1 atmosphere of pressure. So I have P1 and V1 and P2 and V2. So I'm going to be using Boyles Law. P1 V1 equals P2 V2. And I'm going to isolate the variable that I'm trying to solve for, which is V2. So I'm going to divide both sides by P2. So V2 equals P1 V1 over P2, which equals 0.974 atmospheres times 125 milliliters over 1 atmosphere. And that is 122 milliliters. Okay, I have 3 significant figures in both of these numbers, and this 1 atmosphere, this is a definition. So this is infinite significant figures, okay? So just 3 significant figures in the answer.